As usual, here are the chapters so you can jump to any section of the video you want. The basic principles of relays and solenoids are very simple. They're both electromagnets. So, as a brief introduction, if I wrap a bit of wire around this nail, and to speed things up, I think I might add my battery drill to the thing. And cut it off, black. Now I just need a battery. So that's my electromagnet. I'll strip the ends of the wire. And when I complete the circuit, this will make the nail magnetic, and I'll try and lift some staples out of the box. So 1, 2, 3. That's a basic electromagnet. Well, to make this into a relay, all you need is a pair of electrical contacts with a bit of steel attached. So then, if I bring my my little magnet anywhere close. Oops. So a relay is really just an electromagnet with a pair of contacts attached. A solenoid is equally simple, really. But instead of wrapping the wire around a bit of metal, bit of iron or a bit of steel, you wrap it round a tube like this, and then put some steel inside the tube, and then when I complete the circuit, with any luck it'll suck the iron into the tube. And that's all there is to it. So really, relays and solenoids are both just types of electromagnet. Well, one of the most common uses of basic electromagnets today is for door locks. So this part will be on the frame and this part will be on the door. Not so much in homes, but in offices and factories and that sort of thing. The coil itself is embedded in this plastic, and then the steel wraps all the way round, down the bottom and up the sides. So when it makes contact with the door, there's a sort of magnetic circuit that flows all the way around, and that makes the attraction a lot stronger. And it is very impressive. This works only at 24 volts and 200 milliamps, but you'll see. So if I connect it up now, lock the door as it were. Now, the spring scales. I shall try and unlock it by brute force. One more try. No, I can't do it. So it is very impressive, but this force drops off very rapidly with distance. So I've got some shims here. They're only about 0.75 of a mil, less than a millimetre. So I'll put the two shims on and then put the lock back, connect it up again. Gosh, that was practically nothing. I was expecting it to be a bit better than that. Where have we got to? Yeah, about 50 pounds. And if I double that up, oops, so now I think we'll be about 1.5 mil spacing. So 1.5 mil is not a lot, but the force, I think you'll find, has gone almost down to nothing. Yeah, only about 10 pounds. So electromagnetism declines rapidly with distance. It's a short range attraction. I think theoretically it's actually supposed to decrease with the fourth power of the distance. So if you double the distance, the attraction goes down by 32 times. Although the force falls off very rapidly, the really strong attraction when it's actually in contact is still very useful. One gadget that I use a lot that makes use of this effect is electromagnetic clutches. There are many different sorts. This is the basic idea. The actual electromagnet is in the back bit here. That doesn't rotate. But when the electromagnet comes on, it magnetizes this steel in front. And then the other part is this steel disc that in this case is fixed to a sprocket wheel, and that would normally sort of hover about 0.5 mil away. But if I now connect up the clutch, you can see the gap actually just goes away, and now this bit of steel will be completely locked with the sprocket wheel. This is a clutch that I've connected up to a mechanism. So at the moment the sprocket wheel is completely separate from the hammer, but when I engage the clutch with this switch, so you can use them for all sorts of things really. So put your ear to the intercom for some confidential advice.
As a qualified doctor, I can help you boost your performance. Insert a foot into the cowl at the bottom of the machine and you will feel a secret raised patch. Simply press down on this during the race to inject more power to your muscles.
3, 2, 1, go! On machines like Supercycle, there's a clutch on both sides, the back of the crank wheels, so that normally the cranks aren't connected to the rest of the machine. When you put your money in, the clutch is energized and that connects to the rest of the mechanism. You can just see the clutch behind the sprocket wheel from a low angle, and you can see at the moment it's not rotating. If I switch it on with a test switch down here, the clutch will now rotate, and you can start to see the bike in there as well. Turn it off, and it won't move again. So somehow I've ended up with a large number of solenoids over the years. I hardly ever use them, so I'm not quite sure how I've ended up with so many. I suppose I just can't resist taking them out of things when I'm pulling things to bits. These two are my two biggest ones. Never found a use for them. And this one is my very, very smallest one. Came from eBay. Well, a lot of these are really quite old. They were at the heart of electromechanical contraptions, their heyday in the mid-20th century. So devices like this, I've no idea what it did. They're 3 separate solenoids. And and they all do move different parts of this system. There were lots and lots of things like this at the time. I rescued quite a few from scrapyards over the years, just things that took my fancy. This one is a ticket cutter, so that's a miniature little guillotine in there. And this one's from arcade machines of the 1950s or 60s. This is called a Pekka payout. So this tube is full of coins, and each time it comes on, it spits out one coin. Again, very satisfying. This is definitely one of my favourites. This is from a Morris Minor car. It's the indicator mechanism. When cars had little arms that flipped up instead of the lights they have now. And it has such a long travel, this solenoid. It works very, very beautifully. The electromechanical mechanisms that I particularly like are things called impulse clock mechanisms. So every pulse I send this clock, the dial moves round a minute, or maybe it's 30 seconds, I'm not quite sure. So these clocks, they would normally be in offices or factories linked to a master clock that would send out the pulses, and these would be slave clocks. So behind, I'd forgotten, I thought they were solenoids, but they're actually electromagnets. Beautiful little things. So I've got quite a few of these. And this is a sort of giant, much more heavily built one, obviously for a clock with much larger hands. So that would be the hour hand connected to that shaft and the minute hand to the outer one. But it's basically just a giant version of the little one. Then there are variations on the theme. This is a wonderful contraption. I don't think it's actually a clock. I don't think it would be accurate enough. But you just connect this. And it keeps going. I've no idea what this was used for. But clocks aren't really made that way anymore. They all now use stepper motors, dial clocks, and dial watches as well. That seems to be the cheapest way to do it these days. Solenoids still have their place in the modern world. Solenoids are used in cars. The starter motors always has a solenoid on the side. If I pull the coil off this one, the coil has actually failed in this one, so I can't show you it working. This is the slug of steel it moves in. So it's a very ingenious design. So this is the car flywheel next to the starter motor gear. The solenoid, as it pulls in, meshes the gear and the starter motor with the car flywheel. But that's not all it does. Now when the solenoid's fully back, it joins these two connections, completing the circuit to allow a current through to the motor that makes it run and actually start the car. Computer hard drives still have a sort of solenoid, a sort of cross between a solenoid and a motor and an electromagnet. You can just see the coil of wire there, and this moves the arm across the disk. It's got a permanent magnet above it and below it. These things are beautifully made and incredibly reliable. And then also the electronics are really clever. the sort of feedback to keep the arm in precisely the right position to read and write the data. Works of art hidden beneath your desk. I actually have an antique one of these that I'm rather proud of. I've picked it up at a car boot sale, but the disc wasn't with it. I don't know what diameter the disc would have been, but it must have been pretty enormous. That's the position encoder on the side there, and the coil, this time with the magnet in the middle of it. So another thing that's not quite a solenoid but has much in common is a loudspeaker. Here it's the actual coil of wire that moves and not the steel. So this one I've cut in half, and there's the coil wrapped around there, tiny little coil, and it slips in this tiny gap in the magnet, a bit like with the door lock. You're wrapping the coil around the magnet, and of course what happens then is that this moves the coil in and out, and the whole diaphragm, and that's what moves the air and makes the noise. Well, this looks quite a sophisticated design, but actually you can make a loudspeaker very, very simply. It's one of those things that just sort of wants to work. So if you start with just some thin enamelled wire, you can get it out of an old transformer or something, and you wrap it round into a coil on a crisp packet. So there's my little coil of enamelled wire, held in place by some double-sided tape. So now you just connect this to the speaker output of any old music player. I think that's all right. And now the final ingredient is a rare earth magnet, really powerful. Slightly buzzy bass. I found that posh crisp packets work a bit better than cheap ones because the plastic's a little bit thicker. You've got a volume control over how close you put it. Well, I still use solenoids occasionally in my machines.
Bedbugs are back. They were almost wiped out in the 20th century, but today's pesticide bans and increased air travel have led to a population explosion, and they're now able to feed everywhere.
Delicious, what a lovely flavour.
It looks as though our heroes are done for, but just as they are about to drown...
So in these scenes, solenoids move the bed bugs and the contact lens. And then they move the objects on the bathroom shelf.
Dazed and confused, they finally regain consciousness in a very different place.
So actually on the bed bugs, I think I needed the solenoids to push rather than to pull. So all the solenoids I've shown you so far pull the slug into the centre of the coil. But you can get ones that have a rod all the way through, so that they, at the same time as they're pulling the main slug in, they push this rod out the other end. And I think that's often very useful. So much so that I quite often convert solenoids to do that. So I would drill a hole in the central lump of metal and add a rod, and then drill a hole through the back of the solenoid frame, and then you end up with a solenoid that can push as well as one that can pull in. One of the reasons I don't use solenoids much is because they're the pulling power decreases with distance, a bit like electromagnets, but it's not quite as bad as electromagnets. But with this example, this one is 3/4 of the way in at the moment and has a really useful about 10 pounds of pulling power. Very impressive. If I move that out a bit, so now the coil is about halfway out. It'll no longer pull at 10 pounds, maybe at 8. Just, yeah, at 8. Still not bad. If I go down to, that's about 3/4 of the way out. So, £7, £6, £5, 4. I think that went about £4. Let's just try that again. Maybe a bit less. Yeah, about £3.5 then. So now if I have it fully out, well, not fully out, there's still a chunk of the coil in, but this is as much as you'd ever want to use it. The force is now, oh, it's actually a bit better than I was expecting. Yeah, about 2. Yeah, not as bad as electromagnets, but extending the travel 4 times reduced the power, yeah, by about the same amount really. The power just gets stronger and stronger as it gets more fully into the coil. And it's just something you have to live with and work with when using solenoids. One way to increase the power is to increase the voltage. You can't for long or it would burn out the coil, but for a short period you can run it at 2 or more times its voltage. And this one has a pair of contacts that automatically disconnect as it pulls the solenoid in. So you start with a high voltage, and when these contacts break, it just continues with a lower voltage powering the coil and it won't get hot. But it means that when the coil is further out, it still has a higher pulling power. I had trouble with a solenoid on Supercycle. It's a little thing down here. So what actually drives the wheel round as the cyclists race is a little friction drive here, rubber wheel running on the aluminium. And when they get to the end of each stage, this solenoid bumps into the steel down the bottom, and then the friction drive doesn't work. So it was all right to start with, but after a while the solenoid wouldn't retract. There's quite a bit of side load from the steel bumping into the side of the solenoid, but I was surprised how weak it was. So I had to increase the voltage in the end from 12 volts to 48 volts. I thought it would be okay because in the PLC my software was only letting it come on for a second. But there was a bug in the software, so it came on for too long and burnt out the solenoid. So this is a replacement. So yeah, you have to be careful of that. Surprisingly, there are also solenoids that work with AC, alternating current. I very rarely use them. I suppose they can be useful. It's surprising in a way that an AC solenoid works at all, because the current's going backwards and forwards all the time, and you might not think you get a constant pulling force. Their construction is slightly different though. It's got lots of laminations. Well, the reason is twofold really. You've got to have a material that can magnetize and demagnetize very, very easily. And you've also got to stop eddy currents sloshing around with the rapidly changing currents. So these laminations have a bit of varnish between, so they're not electrically conductive. That stops the eddy currents. And it's actually a special electrical steel, it's called, that's used to make them, that magnetizes and demagnetizes easily. Transformers are the same construction for exactly the same reason. I think probably the most common use of solenoids today is in solenoid valves. So this is a sort of basic one. It's like a sort of valve or tap just to open the flow of water or gas through from this end to that end, following the arrow. So the solenoid is in this black lump on top. Now if I pull that off, then you have to undo this bit, and inside this is the steel slug that the solenoid pulls in. It's quite a strong spring there, and by doing that it uncovers this hole, and that allows the water or whatever to flow through the valve. A basic valve like this needs a fairly powerful solenoid, so it's quite big, and I think it's about 10 watts, this particular one. So actually most solenoid valves work slightly differently. The solenoids are usually much smaller, and instead of opening the main flow directly, they just allow a small amount of fluid into the valve chamber that uses the pressure of the fluid itself to open the valve. Even washing machine valves are like this, which I explained a long time ago in The Secret Life of the Washing Machine. Simply pass the current through it and the valve opens. The clever thing about these valves is it's just a small cylinder and a small coil, and it has to resist the full force of mains water pressure. So I have to actually put my finger over the edge quite hard to stop the water coming out. Whoops. It does this by using the pressure of the water itself to stop the water coming out. This part is the solenoid, a sort of electromagnet. The steel piston in the middle is attracted by the magnetism and pulled in when the current is switched on. The piston rests on the centre of a rubber disc which acts as the seal. In this disc there are two tiny holes. The hole in the side lets water into the space above the disc, and then the water pressure itself keeps it down. When the current is passed, the piston uncovers the centre hole and lets some water leak out. This lowers the pressure above the disc and lets it pop up and the water flow through. So in this digital world, my collection of relays, like my collection of solenoids, looks distinctly old-fashioned. But again, like solenoids, relays still do have their uses. So this is a basic one, a basic simple design. The coil, I'll just take it to bits. Oops. The coil is in the bottom here, under this blue plastic. This is the contact arm, and the contact's on the end, and they make contact with the fixed contact on this side. The coil only takes about 60 milliamps, and yet these contacts can switch 15 amps AC mains. So that's one use that relays are still often used for, is a small controlling amount of electricity to switch much larger amount. So on all my machines inside there's the PLC logic controller, and then there'll be a row of relays. And actually these relays, they're miniature ones, although they're smaller than the one I was showing you earlier. They can switch the same amount of current, 16 amps, but it's only one set of contacts. There are actually internal relays in the PLC, 5 amp ones, but I prefer for anything over 2 amps to have external relays, so easy to change and check. But also they have these test switches. When you push and turn the little blue button at the bottom, it pushes across the mechanical contact. So if you do the test button, it switches the relay. And I find that really useful for fault finding and generally for testing and stuff, even though the relays cost a bit more than some simpler ones. There's one slightly odd thing about these. These work fine, but it is quite awkward. Sometimes they're very stiff to push and turn. The test mechanism isn't ideal. I used to use ones that were much nicer, made by a different company. There was one to Finder, this was Relayco. They had so much nicer switches, really liked them, easier to use. But these ones, Relayco ones, had a weird fault. After a while, the electromagnet just seemed to get weaker and stopped having enough power to switch the contacts. I've never got to the bottom of it, but I had to strip them out of quite a number of machines and replace them with these Finder ones. Well, a big drawback of relays is that the contacts can arc when, particularly with inductive loads like motors. So here I've connected up, it's about 6 amps at 24 volts. It doesn't arc every time, so I don't know whether... So the sparks don't look that big, but over time this arcing can completely erode the contacts till there's virtually nothing left. So it is a very serious problem. For some things, for AC loads, you can buy suppressors, little bits of electronics to put across the contacts. But for DC, I've found that they're not very effective. So the best solution is the most expensive one, is to use a solid state relay. One like this probably costs at least 50 quid. It's 10 amps, but has very long life and particularly good for things that are being switched frequently, like clock escapements or something like that. Even if the motor's not a very high current rating, I would use a solid state relay. One thing you have to be careful with these is that is to look at the rating, because the earlier ones, till recently the most common ones, switched AC, switched alternating current, and to this day they remain a lot cheaper than the DC ones. So that's the best solution. I mean, you may be wondering why I don't just use MOSFETs to the transistors to do the switching. Well, I did try, but I kept blowing them up. So I thought just stick with things that actually seem to work. You can get big relays. That's another way of doing it, to vastly overrate it. The contacts, that certainly helps. You get really big ones like this. I don't know what this current this is rated at, probably 40 amps or something stupid. In the past, I'd have used a nice mercury relay. This is puddles of mercury that just bridge 2 contacts, make the connection, but you can't use those anymore. So what I tend to end up with contactors. The motors in here that make the chair and the magic carpet move around are 2 of the largest ones in the whole arcade. And this one doesn't actually have a solid state relay to control them. It uses these little things called contactors. They're a sort of industry standard thing for switching electricity. You get them to switch 100 kilowatts, but they've just got two goes, one for the up down and one for the side to side. So this one I've taken to bits. These are the fixed contacts, and this blue bit of plastic moves across from side to side, so making one contact and breaking another contact sort of thing. And the blue thing is moved by, if I pull that out, by this coil underneath. This is probably my very smallest relay, but the ones I use most are ones like this, partly because they're the cheapest. This is a reed relay, slightly different from other relays. It's totally encapsulated, so you can't see inside, but what is inside actually is a pair of contacts, a bit like this, and one of these contacts is magnetic. So if I bring a magnet anywhere near it and watch the contacts very closely, you should see them close. Close, open, close, open. So to make this into a relay, all I need to do is to wrap a lot of wire around it, to make an electromagnet to wrap round the reed, if you like, of the switch. So, I mean, that wouldn't be enough, but that's the general idea, and that is what's inside this little thing. When you energize the electromagnet, that's enough to switch the contacts. Well, the great thing about these is that they need so little current to make them work, only about 10 milliamps, and this is low enough for the transistor outputs of many digital circuits. So, for example, one place where I use them a lot is on my coin acceptors, these cheap Taiwan ones that I get on with quite well. So they have a pulse, 100 millisecond pulse output, which will power one of these. So I actually make up my own little circuit boards to interface with the PLC, because the PLC works at a different voltage, so at 24 volts, whereas these work at 12. So the output of the PLC provides the power through a voltage regulator chip there, and then with the reed relay on this side provides a switched output to go back to the PLC computer. And I find this works very well. But more generally, to isolate fiddly, complicated digital circuits from the rest of the machine is very useful. It just makes fault finding a lot easier. So relays may be simple things, but they can do some quite clever tricks. So in this circuit, the red wires are just the circuit to the coil of the relay, and the black wires are the circuit to the motor that comes through here, up through the relay contacts and back. So that's a simple circuit. But by just adding one extra wire from the motor to the normally closed terminal of the relay, the motor will now stop dead when I remove the contact. And that's because when the relay switches off, it now forms a short circuit round the motor, and then the back EMF has the effect of breaking it very, very rapidly. Take it away. I went into more detail about this in the episode on motors, but it is extremely useful to be able to stop a motor or a mechanism in a very precise position. This is another very useful relay circuit. This time, that's the main switch, that's on already. This time I've wired this switch in parallel with the normally open contact. So if I momentarily make this one, the relay will stay on now because the current can flow through the relay contacts. And it will stay on for a long time, or as long as I want it to, until I break the main switch here. Well, this is also very useful, or used to be very useful to me. When I made my first coin-operated machines, I used this to trigger the mechanism to get it working as the coin fell down a slope and triggered a micro switch. Another useful relay circuit is for reversing motors. So here the power supply is the red and the black, and on this side the positive is connected to the normally open contact and the negative is connected to the normally closed contact. On the other side of the relay it's the other way round. The positive is connected to the normally closed and the negative is connected to the normally open. The yellow wires are the ones that come via these grey wires, and they go out to the motor. So what this is doing, it's swapping over the polarity. When I energise the relay, it'll go back the other way. It's actually not generally a good idea to slam motors into reverse like this, because the arcing is actually even worse than stopping or starting. The proper way to do it, which I do in my arcade machines, is to first stop the motor, then to activate the reversing relay, and then restart the motor. You know, you only need to have a sort of 0.1 or 0.2 second delay between each step, but it greatly reduces the arcing. Relays can actually do complicated logic. Old pinball machines had large arrays of relays under the playing board. And there were even entire relays computers in the 1940s. The German Konrad Zuse is credited with the first programmable fully automatic computer powered by relays, but there were a number of others, like this Bell Labs ballistic guidance computer that was said to do the work of 20 human calculators. One relay logic circuit I still use occasionally is this binary to decimal converter. Each relay is a binary digit, and different combinations output their decimal equivalents. So if I run out of outputs on my PLC logic controller, this gets me a few extra ones for free sometimes. Logic circuits like this, combined with holding circuits, called flip-flops in computing language, were the basic building blocks of the old relay computers. Actually, the stepladder programming language for PLCs, programmable logic controllers, the things I use, it was originally developed for engineers who were used to hard wiring their programs with relays. I decided to end this video with what's probably my favourite use of a solenoid. It's part of Novelty Automation's donations box. So after making a donation, you're invited to participate in an academic research project investigating the link between generosity and willpower. So if you're brave enough to accept the terms and conditions, once you've got the helmet on, you just have to concentrate on the glass as hard as you can and will it with the force of willpower to smash to pieces. Well, having watched this video about solenoids, I'm confident you'll be able to work out how the trick is done. Bye!